Hey everybody, welcome back to another round of astronomy. And yeah, let's get going. The last thing that we have to talk about is the Doppler effect. If you prefer, we could say using light to determine the speed of an object. Ready for it? Yeah, let's get at it. So, question for you. We'll start off with this. Let's say that you have a generous friend who is standing a distance away. And they are generous because they are going to throw a piece of candy at you every second. So the frequency that they throw a piece of candy is 1 piece per second. Question for you. At what frequency do you receive the candy? Yeah, you got it? Yeah, good. So if your friend is throwing a piece of candy every second, after you receive that first piece of candy, you're going to continue getting a piece every second. Okay? Nothing fancy here yet. Okay? But here comes the corollary question. Okay? Let's say now your friend starts moving backwards, okay, as they throw their pieces of candy. Okay? Now what happens to the frequency at which you receive the candy? Do you get pieces once per second, more than once per second, or less than once per second? Yeah, good. Because your friend throws a piece of candy, they move backwards, and they throw another piece of candy. That second piece of candy has a longer distance to travel. And because it has a longer distance, a longer time, which means you're not going to receive your piece of candy every second. It's going to take a longer time, and so you're going to get less. You're going to have to wait a longer time to get the next piece. So on average, you will get less than 1 piece a second. Good so far? Keep in mind, your friend is still emitting candy at once per second. The fact that they're moving backwards means that you receive candy less than 1 piece a second. Okay? And that effect is what we refer to as the Doppler effect. It's not that your friend is throwing candy at a different rate or a different frequency. It's the fact that because there is movement, relative motion between the source, your friend throwing the candy, and the receiver, you, that causes the frequency that you receive the candy to change. And indeed, rather than thinking about pieces of candy, let's think about sound waves. Okay? And you'll notice in this clip, as it moves towards you, you as the receiver are going to get those sound waves at a higher frequency. Okay? That's like your friend throwing candy at once per second and moves towards you. You will receive candy more than 1 piece a second. Okay? But as the train passes and starts moving away from you, you'll notice that the frequency drops. So let's get an idea here. Right, it's a substantial drop. Okay. Now that, of course, is in terms of frequency, sound. Okay? And I'll highlight this. This is motion. If it's moving towards you, you'll receive it at a higher frequency. If it's moving away, you'll receive it at lower. Okay? Now, of course, in astronomy, we don't use sound to, measure the Doppler effect. Okay? We use light. So the idea is this, okay? We know, for example, the specific wavelengths for hydrogen emission. Okay? If we have hydrogen, the element hydrogen, it has 4 very specific emission lines in the visible spectrum. Now, we can go into a lab and measure very precisely the location of those spectral emissions. I've labeled one here, 656.28 nanometers. This is sometimes referred to as the hydrogen alpha line. Okay? Now here, imagine this for a second. Imagine that you have something made of hydrogen which is moving away from you. That object is emitting light. We'll say, I don't know, let me think of a large object in space comprised primarily of hydrogen that emits light. Stars. Okay? So hydrogen is very abundant in the universe. Stars, for example, are primarily made out of hydrogen. So imagine for a second that you have a star which is moving away from you. This hydrogen alpha line, will it be seen at higher frequencies or lower frequencies if it's moving away from you? Good, a lower frequency. Okay. Next question. Thinking about wavelengths now. How is a frequency and wavelengths connected? How are they related for light? Yeah, this one's a little harder. Remember, the speed of light is given by the wavelength of light times the frequency, excuse me, that's a terrible F, of the frequency of light. Okay? So if the object is moving away from you, the frequency of light goes down. What does that mean happens to the wavelength? The wavelength must go up. If the frequency goes down because it's moving away from you, the wavelength must increase. Next question. Longer wavelengths. Is that towards the red end of the spectrum, or is it towards the blue end? And this is why I asked you to memorize those 2 numbers. Remember, I asked you to memorize 400 nanometers, and I asked you to memorize 700 nanometers. This is in part why I asked you to do that. Longer wavelengths correspond to the red end of the spectrum. Okay? So here's where it is. We have an object emitting light, an object made out of hydrogen emitting light, moving away from you, lower frequency. Because the frequency is lower, that must mean that the wavelength is longer. And longer wavelengths correspond to the red end of the visible spectrum. We therefore call such a shift a red shift. Conversely, let's say for a moment that the star is moving towards you. If it's moving towards you, the frequency of light that you receive will be slightly increased. Well, if the frequency is slightly increased, that means the wavelength must be slightly shorter, and smaller wavelengths are towards the blue end of the spectrum. And therefore, we call such an object blue shifted. Pretty cool, huh? Okay, so let me give you an idea about how can we use this. For example, you can use this not only to determine whether an object is moving towards you or away from you, but we can also use it to see the rotation of objects. Displayed for you here is a picture of the sun, and you notice it's falsely colored. Okay? It is falsely colored in order to visually represent the shifts in the hydrogen alpha line. Hydrogen alpha line. Okay? And based on those shifts, okay, and it's not by accident they chose blue and red, based on those shifts, you can say that the left side of the sun is rotating, is moving towards you. The right side of the sun is moving away from you. And of course, the central region, we'll say right here, is not moving either towards you or away from you. It's actually moving perpendicular to you. Based on that, you can get an idea, left side coming towards you, right side going away, and you can get an idea about how the sun is actually rotating. Cool, right? Well, let me go a little further. How about, okay, so towards and away. How about this? Okay. What we are looking at here is a distant, probably spiral galaxy out in space. Up top, the picture of the galaxy. Down at the bottom, we've got, again, on the horizontal axis, the wavelength labeled in nanometers. And on the vertical axis, what we are measuring is distance from the center of the galaxy, the distance from the central bulge. Okay. Well, first off, we can get an idea. Here's the hydrogen alpha line, and we see from the chart, I'll draw the line down, 660, 661, 2, 3, 4, 5. Okay, so this central bulge, the hydrogen alpha line, is located, let me get a different color here so we can see it better. The hydrogen alpha line is something like 664 point, I don't know, we'll call it 0.7 nanometers. Okay. Well, remember the hydrogen alpha line, I'll put it here, should be at 656.28 nanometers. In other words, the central bulge of this distant galaxy, red or blue shifted? Yeah, longer wavelengths, red shifted. The central bulge of this galaxy is moving away from us. Well, we can keep going. Let's see up here, right? We notice that this is the central bulge, but with respect to the central bulge, you can tell that there's a region of the galaxy, let's say up here, which is shifted even more than the central bulge, right? Right here, maybe it's at 665 nanometers. Or there's a location below, right, which is shifted to the blue end of the spectrum with respect to the central bulge. So we have an idea even further. Because it's shifted even more to the red end of the spectrum, it must be moving away from us even faster. So the top is moving away from us, whereas the bottom is moving towards. So we have an idea about both the speed of the central bulge, whether it's going away from us or towards us, but also the rotation of the entire galaxy. Bear in mind, something like the Milky Way galaxy completes a full rotation in something like, I believe it's on the order of 50 million years. I gotta double check that. But I wanna say it's on the order of 50 million years. In other words, even if this is off, right? It's not gonna be like 1 year or 2 years. It's gonna be hundreds of thousands of years, very easily. We do not have the ability to sit there and actually see the physical motion of the galaxy. It just takes too stinking long. Okay? We still have a way of measuring it. We can say, yes, for certain, that galaxy is moving, it is rotating, and we can even say, by how much? Pretty cool, right? Okay, qualitative. Give me an idea. Which star is moving towards the observer? So I've given you a stationary star for a reference. Tell me, which star is moving towards the observer? Go. You got it? Yeah, good, good, good. Again, practice. The idea is that if it shifted towards the blue end of the spectrum, which I've conveniently labeled, then it's moving towards the observer. So what we need to do is simply see Okay, well, those two, star A and star C, are shifted away, go towards the red end, so they can't possibly hit. It must be star B. Well, how about this one? Which star is moving the fastest? Yeah, good, good, good. And recall, the larger the shift, the faster the object must be moving. So the size of the shift is indicative of how fast the object is moving. Let's go ahead and quantify that a little bit more. Okay? So I will now give you the equation. Okay? And let's walk through what each of these means. You should already know what C means. C is reserved and represents, the speed of light. Okay? A mere 3 times 10 to the 8th meters per second. Okay? No problem. Next, okay? The next one is, we'll say V. V is the speed of whatever object you're measuring. Okay? Speed of object. Okay? Now, for the purposes of this class, we will assume that we, as the observer, are stationary. Down here, we'll say lambda stationary. That is the wavelength that a number should be at. In other words, for the hydrogen alpha line, H alpha, lambda stationary should be that 656.28 nanometers. This is the value that you would measure if the object were stationary and you were stationary. Okay? Sometimes this is called the lab wavelength, the wavelength that you would just measure sitting there in lab measuring the emission line. Okay? The last one is this delta lambda. This is the shift. Okay? So, for example, if the object's moving towards you, you need to measure how much the wavelength has been shifted by. So you have what the wavelength is measured from your observation, what the wavelength should be, and the difference between those is what's known as the delta lambda, the shift in the wavelength. Well, let's get some practice. So displayed for you here, I have 2 absorption spectra. Okay, you notice that this is called normalized flux. You could just simply, let me scratch that out, just think of this as being intensity. So you see that there are some drops in the emission of these 2 stars. So I have Arcturus and I have the sun. Question for you, go ahead, pause the video, take a minute, but let's find out how quickly Arcturus is moving with respect to the sun. You got it? Good, 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 good. And now hopefully you can see an idea about what I mean by delta lambda, the shift. Let's go ahead and assume that the sun is stationary. So this is where the absorption line should be, and this is where it's measured to be for Arcturus. So the difference between those two would be the shifted value. Now, the thing I'll point out to you is that you'll notice that the shifted value will be roughly, proportionally will be the same. Okay? So you might say, which one do I need to look at? Which pair do I need to look at? It doesn't matter. Okay? Just be consistent. Now I, for example, decided to choose this middle pair. And the reason I chose the middle pair was because that red line falls almost exactly on 884. Okay? So it makes my life easy. That's the only reason. Okay? Now, how do I get the shift? I'm asking you to read something from a graph. So here's how I did it. I say, okay, let's say, for example, this represents 0.5, a change of 0.5. And I'm going to say that it's roughly, I'm going to split it into thirds. Okay. So really what I need is the shift. I'm going to estimate lambda shift as being something like, the shift in lambda is something like 0.5 divided by 3. For me, I had something like 0.17 nanometers. Well, at this point, we're off and running like a bale of turtles. Okay? We have estimated the shift in the spectrum of Arcturus with respect to the sun. Okay? So I can now find the speed of Arcturus. I have rearranged the equation, just simply multiplied both sides by c. Okay? And now we're prepared to throw in our numbers. Okay? We have our shift, 0.17. Okay? And here I will put, oops, excuse me, I seem to have lost my oh, there it is. I've lost my cursor. I've neglected to put in nanometers here. Down here, we also have nanometers. And we can say, oh, goody, goody. Because I have nanometers in the numerator and nanometers in the denominator, those cancel out. Okay? And, of course, we have 3 times 10 to the 8th meters per second, the speed of light. Okay? Well, let's go ahead and crank out. And we get something that says that with respect to our sun, Arcturus is moving at something like 57,000, almost 58,000 meters per second. Right? About 58 kilometers a second. In miles per hour, or that's about 40 miles every second, which is wicked fast. Keeping in mind, this is an entire star, right? This isn't just like, like a car or a bullet or a rocket. This is a huge, massive star moving at this speed. Okay, so to summarize, we've got 3 different observables for light. How bright, or the intensity, or the luminosity, we'll keep playing with that. We have the color or wavelength, and we have the speed of light. And from that, we have been able to infer other ideas such as temperature, composition, distance, and also speed. And now we'll start using those ideas as we progress through to get an idea both about how stars are formed, how stars die, and also the size of our universe as well as the fate. So I hope you're excited. We're really starting it. We've laid the groundwork for everything we need to really start getting into nitty-gritty details of what's going on in our universe. Hey, I thank you for your attention. Keep up the good work. Bring me questions, and I'll see you next time.